All right, so we're going to kick off today. Something I always find kind of interesting with forces, and that is called the gravitational force near Earth. All right, so what we're going to do here is we're going to distinguish between two different words that are commonly used in real life, but in physics, they mean something different, and often they're confused as being the same thing. And those two words are mass and weight. Now, mass is the quantity of matter in an object. All right, so we all have mass. So if the amount of matter in an object remains the same, its mass stays the same. Okay, so that doesn't mean a whole lot right now. Now, the other word is weight. Weight is the force of gravity on an object. So that's where we're dealing with forces here. And that force is called Fg, right? The force as the result of gravity. Now, to find weight, or the force of gravity acting on an object, we have mass times g, where g is the acceleration due to gravity. And so if a person here in example 1 has a mass of 75 kilograms, find their weight. Well, that is where we would just look at finding Fg, which again would be their mass, 75 kilograms, times the acceleration due to gravity. And so your Fg, your force of gravity, or your weight, let's see, I multiply those numbers, would be 735 newtons. Now, just a little side note here is that if you look at the force of gravity on the moon, so this is the force of the moon. It's the same formula, but here's the difference, is that we would go 75, the mass, but every planet, or I guess every moon or planet, has a different G value. Earth, it's 9.8, and on the moon, it is 1.62. And so if I multiplied those together, you'd have 75 times 1.62, 121.5 newtons. And so what happens is that the mass that you have on the moon and on Earth does not change. The mass is going to be 75 kilograms no matter what planet you are on, but you're going to weigh different. On Earth, you'd weigh 735 newtons, but on the moon, only 121.5 newtons on the moon. And that is why you see people bouncing around on the moon, because the acceleration or the force of gravity acting on them is not as great. All right, and now if you go to, say, Jupiter, which you can't, and you can't stand on the planet that we know of, but if you could, because Jupiter is so big, you would weigh 3 times as much. So a 200-pound person who went to Jupiter would feel like, when they're walking, like 600 pounds. So when we go, to different planets, as we're starting to visit Mars, we have to take that into account, because your spine doesn't react very well when all of a sudden gravity changes. All right, on that note, and again, here's a kind of funny thing, is on the moon, because the force of gravity is less, people who go out in space and walk on the moon for a while tend to be taller when they come back, because their spine stretches out. Now, it goes back to normal after a little while, but it does stretch out. They get a little bit taller. I should go there for a bit. All right, now, example 2. An 80-kilogram person is standing on a bathroom scale inside an elevator, which displays your weight in newtons. What is the reading on the scale when the elevator is traveling at a constant velocity? All right, so I want to explain this a little bit, or a whole bunch. Here is us, or this person, an 80-kilogram weight. And what you have is the force of gravity acting on this person. And now, what's your bathroom scale? Well, actually, we can find that force of gravity just like we did before. Mass times g, the acceleration due to gravity, which again would be 80 times 9.8. And so we take 80 times 9.8, and I get 784 newtons. I'm going to move that. There we go. Now, here's what happens with your bathroom scale. It feels that force, and it applies Newton's third law, where it applies a force equal in magnitude, opposite in direction, which is called our normal force. All right, and our normal force would also be equal to 784 newtons because you're just standing there and your net force is equal to 0. And so your bathroom scale tells us this force, only it displays it in pounds. All right, so if you're traveling at a constant velocity, Newton's first law, which means you're just moving, you're not changing your speed at all, it means your net force is equal to 0. And so in this case, our bathroom scale would read Fn, because that is our bathroom scale. I should write that down. And so it is the 784 newtons. That's what you would weigh if you're moving at a constant velocity, which means F net is equal to 0. The same applies if you're just standing there and you're not even moving. You're at rest, because again, your F net would be 0. Now, let's change it up a little bit. All right, so again, here's what we use too, is kind of a great way to look at it is our F net in this situation, which is equal to 0, is because we are adding Fn plus Fg, right? Because they're in the opposite directions, they cancel each other out. Now, here's a little bit of a different scenario. This time, we're in an elevator again. I'm all about the elevators. We're going up. We're accelerating up. So now, because you're accelerating, your net force is not equal to 0. So your F net is equal to, well, Newton's second law, ma. All right. Now, it's still, in terms of our bathroom scale, the scale is still going to push up. And gravity, I don't have vector symbol here, so I should do a minus, I guess, is minus Fg. All right. Or I guess, we'll leave it as plus. All right. So, whoa, construction. All right. So now I can find ma. I know the mass of this object is 80 kilograms. Plug that in. Our acceleration is 2 and it's upwards. So I'll put a positive 2 equals Fn. That's what we're trying to figure out. We're trying to figure out how much is the bathroom scale going to push up. All right. And our Fg, well, we already found that. That's our 784 here. All right, so doing some math, 160 is equal to, whoa, I see what I messed up here. Minus, that should be a minus sign because Fg is acting down. Good, got to take account into the minus signs. So now I'm going to move that minus 784 over to the other side. So now it becomes a plus 784 is equal to our Fn, which again is our bathroom scale weight. And so if you're in an elevator and it's moving up, you're going to look like you weigh more. I take 160 plus 784. I get 944 newtons. So for some of you who perhaps live in a condo or an apartment building and you have an elevator, try it out. You'll see that at the beginning, when your elevator is accelerating, not when it's moving at a constant velocity, the scale will change. Now we're going to look at it the other way. Accelerating at a rate of 2 meters per second squared, but down this time. All right, so I'm going to use the same formula and see what our scale does. Now, my guess is if our elevator's on our way up and we weigh more, well, on the way down, we're probably going to weigh less. But again, F net in this situation, because we're accelerating, it's going to be equal to ma, which is not going to be 0. And again, we have Fn plus our Fg. All right, now again, mass times acceleration. Well, our mass, again, it hasn't changed. It's 80. Our acceleration, we're on our way down this time, so minus 2 equals. We have our Fn, and again, our Fg, it's a downward, so it's minus 784. All right, so this time, it's going to be a little bit different. I got minus 160 on that side. Now, again, I'm going to move that minus 784 over to the other side. It's going to be a plus 784, and that is going to equal our Fn, which is our scale weight. And if I put those two together, And as I guess, this time we're going to minus 160 instead of add 160. And so we're going to weigh less. In fact, we would weigh 624 newtons. So if you weigh yourself in a moving elevator that is accelerating, which means changing speed, you're going to change, your weight will change, which is kind of neat. Again, if you live in a condo or an elevator, try it out. All right, now we get to the next part. Because I talked about the force of attraction of gravity, and that's towards Earth. And so what we're going to look at here is the law of universal gravitation. Anytime you got two things, they are attracted to each other. So every object in the universe exerts a force of attraction on all other objects, near or far. Just like, for instance, in a big kind of concept, the Earth has a force on the moon, but yet the sun has a force on Earth. And we have forces between each other, but they're so small we don't even notice. Now, the forces of attraction decrease rapidly as objects move apart. That's one factor is their distance, and the greater the total masses of the object, the greater the attraction. And that's, again, why I used the Earth and the moon and the sun, because those things are noticeable. All right, now we have a formula. Fg. This is force of universal gravitation. So that's a big capital G. And it's equal to big G here, M1 times M2 divided by D squared. That's a D squared. All right, now what do all these things mean? Well, first off, this big G is a universal gravitation constant, which is 6.67 times 10 to the negative 11. All right, M1 and M2, because we're talking about the attraction between two objects. Well, those are, in fact, just the masses of the two objects. All right, and lastly, D, well, that is the distance from the middle of one mass to the other. All right, now, how does this formula come into play? Well, let's check this out. So this comes back to what we just did. What is the weight of a person who is on Earth's surface, who has a mass of 80 kilograms? Well, we already figured that out. Now, here's the key here. Here's the difference here. It's right on Earth's surface. So we just have this simple little formula that we just went through, F little g, all right? And it's equal to M times G, mass times gravitation. And we have an 80, right, for the mass. And acceleration due to gravity is 9.8. All right, and I believe I again get 784 newtons. All right, we had that before. Now, here's how I'm going to change it up. All right, so here's our formula we're going to use up there. Is now I want to know what is the weight of a person who is flying on a plane that is at an altitude of 20 kilometers above Earth's surface and has a mass of 80 kilograms. So the exact same situation, but now I'm saying that the distance, we're way up in the air here, 20 kilograms altitude, so much farther away from Earth. So that's where we're going to use our formula here when we are drastically far apart, or we just have two objects that don't even happen to be a person or Earth. All right, so I have G times M1 times M2, again, divided by D squared. Now, the mass of, well, G, our G value, that is a constant. That's the one I put down there. That's 6.67 times 10 to the negative 11. All right, M1, that's our first mass of our person here, is 80 kilograms. All right, M2, this object we're attracted to, because again, we're looking at the force of attraction between two objects. Well, we got our person and Earth. And let's see here, our Earth is going to be 5.8 98 times 24, or times 10, sorry, 10 to the power of 24 kilograms. Big, obviously. All right, and now our radius of Earth. So again, we have this person up here. The radius of Earth, we got to count the fact that that's the distance from the center to the outside of Earth. And then we have another 20 kilometers on top of that. All right, so we got to be in standard units here, which our distance is going to be. So we got 6.38 times 10 to the power of 6 plus that extra 20 kilometers. But again, I got to have it in the same unit. So that's there's 1,000 kilometers or 1,000 meters in a kilometer. So that'd be an extra 20,000 meters. All right. So our distance is going to equal, let's see, I add those two together. And I believe I get 6.4 times 10 to the power of 6. All right. All right. So now I finally got all my values here. I'm going to substitute in. So the force of attraction between these two objects. We have I'm going to try to write neater here. Let's go with a 6.67 times 10, and I'll put the negative 11 in after here. Let's go with some space. All right, times our mass. Our mass, first mass, which is just a nice 80, times our second mass, which is 5.98 times 10, and this time it's to the power of 24. I'll put that in. All right, so again, we have a negative 11 here, a power of 24 here. And down below, we have, 6.4 times 10 to the power of 6 squared. All right, now this is, I find the thing that people have struggled with the most here is doing your calculator. All right, and so, well, you can just simply, I'm going to show you two different ways. If you can just type this into your calculator, the top here. So we have 6.67 times 10 to the power of negative 11 times 80 times 5.98 times 10 to the power of 24. You will get 3.19 times 10 to the power of 16. All right, and if you properly type into your calculator 6.4 times 10 to the power of 6 and you square it and you do it correctly, you will get 4.096 times 10 to the power of 13. All right, and then I divide those two, and if you do that correctly, because again, this is big time calculator stuff, I get 778.05 newtons. All right, so that's the first way to do it. Now, before I go show you the second way that I do it, or you'll notice that our FG formula, our simple F little g formula, was 784 newtons. But because we're up such a high distance, 20 kilometers up, the attraction between Earth and us is actually affected. And in fact, I think we kind of know this because as you rocket off into space, once you get to space, you weigh nothing. And so as your elevation increases over and over and over again, eventually your weight decreases down to nothing, where you're floating. And this formula shows that. But again, we can find the force of attraction between any two objects. I just decided to pick Earth and people. All right, now, again, I said I was going to show you a different way of doing this. Whoops, FG. So one way that I do it, I'll start with the example down the bottom here is, I do the powers of 10 together. So in this case, 10 to the power of 6 squared is 10 to the power of 12. And then I'll square the number. So if I take the number, this is how I do it in pieces. Does it take longer? Yes. Does it make sure I always get the answer? Yeah, it does. And I get 40.96. All right, now up here, what I do is I do the same thing. So I take my powers of 10 using my power rules. So 10 to the power of negative 11 times 10 to the power of 24 is times 10 to the power of, well, you add the exponent, so I'm going to have a positive 13. All right, then I multiply my numbers. So I have 6.67 times the 80 times the 5.98, in which case I get 3,190.93. All right, whoops, 93. All right, now what I'm going to do is multiply the number or divide the numbers. So I've got my 3,190.93 divided by 40.96. And I get 77.9. All right, but then I have my powers. Power using my power rule. I have a power divided by a power. I keep the base the same. Subtract the exponents. 13 minus 12 is 1. So basically I times 10 and I would get 779 instead. So there's just two ways of showing you how to do it. All right, so again, I always find, like I said, the calculator is the big issue on that one, on that formula.